Okay, so it's about time. All right, welcome back to DSP. All right, so today we will just use this hour to catch up on lecture, I suppose that the second midterm will cover from where we left last time for the last midterm exam until today's lecture. Okay, but including the next homework though. Okay, so let me be clear that because our homework follows our lectures, right? So part of the exercise in the homework will show up in your second midterm. So let me be clear about that because some people were arguing with the TA last time. So we probably were not 100% clear. Yeah. Homework number 5, content in homework number 5, the next homework, which hasn't showed up yet. Okay, the next homework's content will also show up for the second midterm, which is scheduled to happen 2 weeks from now. Okay, not the next Wednesday, but the Wednesday after that. Okay, yeah. Okay, yeah. So today's topic will be this new lecture, and I have the title of all pass and high pass and bandpass, different ways of allowing components at different frequencies to pass through the filter. So a bit of a highlight: all pass is a kind of filter that has a constant gain. The gain where the magnitude response is a constant across all frequencies. That's what all pass means. And for high pass, I want to just share with you a simple trick. Okay, a very simple trick which I'm just going to write on right here. So we'll briefly mention. This is a very simple trick. Suppose that h of n is a low pass filter, is the impulse response of a low pass filter. Okay, then we simply define g of n to be by just minus 1 to the nth power, h of n. And this will give you a high-pass filter. Okay, very simple, right? Just multiply your impulse response by changing the sign, the sign of every other sample, changing the sign of every sample. 正负号交错 change the sign of every other sample, that will give you a high pass filter. Okay? If h of n is low pass, then g of n defined as such is a high pass filter. So you can try to think why this is the case, and we'll cover it. So it's a very simple technique that I recommend that we can all keep in mind whenever. So it suffices that we've been focusing on low-pass design previously, right? Until yesterday, we are all about low-pass filter. And I did that because I knew that simply by using this, we can turn a low-pass into a high-pass. We can transform a low-pass filter into a high-pass filter. So it's pretty easy. So I want to share with you that this is something we want to keep in mind. Okay, So that's probably a relatively simple topic. But today, probably a more tricky topic is all-pass system. How do we design a system, perhaps with poles and zeros, so that the gain is constant? The magnitude response is constant. Of course, the phase may vary, right? If both phase and magnitude response are constants, then it's trivial. But how about designing a system with constant gain while allowing the phase to accumulate across frequencies? So there are such a class of systems that we call all pass, and we need to talk about it. Okay? The system indeed has some very nice properties. So I want to spend this lecture and mostly focusing on the existence of such kind of systems, all pass, and we will prove that indeed by putting the zero and poles in a smart way, right? By putting the zeros and poles in a smart way on the z-plane, then we can achieve the property of having a constant magnitude response. Okay, All right. So to begin with, the all-pass system, the simplest case. In the simplest case, 最简单的情况 in the simplest case, And then all-pass system has one pole and one zero. One pole and one zero. If a system has one pole and one zero in some kind of locations, and the keyword here, the blank, is reciprocal. That's two. Yeah. Reciprocal. Okay. Reciprocal. 倒影的, yeah. If you will, in Chinese. It's kind of an image, yeah, image locations, yeah. We'll explain what does it mean to have for two locations to be reciprocal, yeah. But we begin with a discussion on a system having one pole and one zero, okay, yeah. The simplest case is one pole and one zero in reciprocal locations. Then we can, as we promised, we can cause it to have a constant magnitude response. And this property, such a property, is called all pass. This is a property that we call all pass, right? Okay, so by reciprocal, now I need to define it, okay? Reciprocal location means that one pole and one zero, of course, we keep the pole inside the unit circle to make it causal and stable. Okay, the pole is inside, and the zero, as you will see, will be outside. Okay, pole inside, zero outside the unit circle, and they occur when they occur at the same angle. Let's say this is an angle, let's say the angle is omega 0. Okay, the angle is omega 0. And let's say if we have the pole inside here, and we mark it with a cross, okay? This is a pole. And this pole location, let's say the pole is located at P equals to R times EJ omega 0. Yeah, that's our pole location. We call the pole P, okay? Yeah. And let's define the zero outside to be the same angle, located at the same angle, but with 1 over r. And let me emphasize that we want r to be less than 1. The radius to be smaller than 1. Keep it inside the unit circle. To keep the pole inside the unit circle so that we have a stable system. Okay? So we put a pole inside at a distance r. That's the radius of r away from the origin. And the outside, 1 over r is going to be greater than 0, right? So this q, the 0, is outside and at exactly this radius of 1 over r. 1 over r. So r here, 1 over r over there for the 0. So if this is the case, then we call the two locations to be reciprocal. Okay? Now that's what we mean. Reciprocal location. We say P and Q are reciprocal locations. P, Q are reciprocal locations. Are reciprocal to each other. That's how we refer to this property. Same angle, but one, the inside and the outside, the radius, their distance, when we multiply the two distances, they become 1, okay? So the radius, r and 1 over r, is reciprocal to each other. 就是导数了, reciprocal. So if we have this definition, when P and Q satisfy this definition at a certain angle at a certain radius r, certain parameter r, then it turns out that we can show this. Then we'll be able to show this. We'll be able to show that a system having a pole right there and a 0 right there, this system has a constant magnitude response. Okay? And if I remember correctly, the constant is 1 over r. Okay, so this is just to tell you the result, the consequence. All right. So at this point, I also want to tell you that, yeah, usually, okay, so then, sure. Here's my, I want to tell you that we don't typically have 1 pole and 1 0 like that. Because most of the time, when we talk about difference equation, all the coefficients need to be real, right? So if we have only 1 0 and 1 pole right there, the corresponding difference equation is going to have complex coefficients. Okay, so this is kind of an exception. Yeah, an exception. So in this case, the corresponding difference equation will have complex coefficients. But please try not to worry about that for now. Okay. Yeah. So so try not to worry about that for now. But let's just say that if the pole is right here, if the pole is right here, the 0 is right there, then we can write the system function as follow. Okay. So here I want to just consistently use the variable p. Where so I'm going to replace a with p. Okay. And here we have. Let me finish writing. Okay, so now you can write down a system function like this. So immediately you notice that Q. So this system, for this system, we have, of course, the pole is at z equals to p. There is the pole, right? We see that. That's pretty simple. And the 0, the system 0 is located at z equals to 1 divided by p conjugate. 1 divided by p conjugate is 1 divided by r e j minus omega 0. So that's 1 over r e j omega 0. Okay, so that's Q. Yeah, that's the reciprocal location. So I can just simply say, just add in here, okay? Yeah. So this is exactly equal to 1 divided by p conjugate, if you will. Okay? Yeah. So the next thing, so now we have, hopefully I have convinced you that this is a system which has a pole at P and a 0 at the reciprocal location. Okay. So next, we want to show that indeed is magnitude response, which is the system function evaluated on the unit circle is going to be constant. Okay, we can show that rather quickly, okay, with this now under this formulation. Having 1 pole right there and a 0 at exactly the reciprocal location. Same angle, but the distance to the origin is going to be reciprocal, 1 over r. Okay? So far so good? So what we are going to show next is to check that indeed the magnitude response, when we evaluate the system function as z equals on the unit circle, then it actually is a constant. Okay? So how do we do that? So now the checking is as follows. So let me just, for some reason, I decide to change my notation. A is P. Okay? P here, P here. Okay, so next, just to follow it step by step. When we evaluate H on the unit circle, we just substitute Z by e to the j omega, right? We substitute z with e to j omega as always. So that's the first step. So that's the first step. And the rest is just to, in Chinese, I would say 就是凑答案. We know that the result we want to prove, right? So now how do we ensure that this is indeed the case? So it's kind of, we can work our way backward, okay? So whichever way you want. It turned out that I would suggest to prove that the magnitude response is a constant. So to prove that this is a constant, okay? So we may need to organize our terms a little bit by some trial and error, okay? So so I'll just give you the good try. My try is to pull out 1 over p conjugate right here, okay? So here it becomes p conjugate subtracted by e to the minus j omega, okay? That's on top. And at the bottom, we have the same thing, 1 minus p e to the minus j omega. And we take the absolute value around the entire expression. So I said this really is about working our way backward. So now, further, how about this does not look so beautiful yet, right? So maybe we need to further try something else. How about we pull out, on top we have 1 over p conjugate. Now, what about we also put this outside to see if we can have a nicer expression, nicer look, okay? So when you do that, the top becomes what? Becomes p conjugate e j omega minus 1. It looks like that, right? With absolute value divided by, at the bottom we have 1 minus p e to the minus j omega, okay? Also absolute value right here. I want to show that this is a constant. I'll show that this is a constant. So what do we have here? This term right here does not matter, right? This term does not matter because it's going to be, it does not contribute to the magnitude. It's simply e to the j omega, right? So we can ignore that, and then just keep taking a closer look at here. So we have 1 over p on the outside. So here I'm going to just separate this term, just isolate this term to the outside of everything, and then focus on the inside. On the inside, on top, we have p conjugate e j omega minus 1. And at the bottom, we have 1 minus p e minus j omega, right? And I claim that with a closer look, this is a constant. This is always equal to 1. If you take a look, this is always equal to 1, no matter what p is. I mean, p is really anywhere inside the unit circle, okay? P is our point, which basically could be anywhere inside the unit circle. But no matter how you choose p, this entire term, when we take the absolute value, is going to be a constant 1. Can you see that? Can you see that? Why? So because we can, again, change the sign right here. We can change the sign. We can change the sign. Put the minus 1 here and change that to plus. Now does it become clearer? Now, after we do that, so on top we have p conjugate. On top we have p conjugate e j omega minus 1, right? And at the bottom, we have P, not conjugate, but E, conjugate, -1, right? So top and bottom are mutually conjugate. They form a conjugate pair. So therefore, their lengths are equal. Okay? Can we, yeah. The top factor is the complex conjugate, now become the complex conjugate of the whatever that's at the bottom, right? So the length should be equal. That's why when we take the ratio is 1. Okay? So yeah, with this rather simple definition, doesn't take up too much time. We've shown that, yeah, indeed, when we put a pole there and a 0 at the reciprocal location, then define our system function. After we define the system function as usual, define the system function the usual way, and we can show that indeed the magnitude response is a constant which equals to 1 over r. Basically, this is equal to 1 over r. Now, r being the length of this the pole. Okay, yeah. Okay. So length, yeah. So now we have a system with a constant gain of 1 over r across all frequency. Any omega. Okay, any omega. Yeah. So we have finished our derivation. All right, so far so good? Yeah. So later I will show you an alternative way of proving that the gain is a constant. Okay? Yeah, later I will show you another way. But now, let's now go back to the issue of the system being not real valued. Okay? The kind of what's not so cool about this system is because we have a pole somewhere inside your circle and a unit and a 0 outside. Then the system corresponds to a difference equation where we may have to have an impulse response which is complex valued, and we don't like that. We don't like the impulse response to be complex valued. Okay? To consist of real part and imaginary part. That's bad. So usually we fix it by this. Okay, we can make sure that that doesn't happen by this. Okay, the idea is that whenever we have a pole somewhere, we immediately put a pole down at the complex conjugate place. Yeah. Okay. But whenever we put a pole here, and immediately we will put another pole at a complex conjugate location. Okay, if the pole has an imaginary part, we will do that. Okay, please do that. Okay, and similarly, we need to have a pole and a 0, and whenever we have a 0 outside, we will put a 0 at the complex conjugate place. Okay, so here is the idea. We begin with the pole here, and we know that the corresponding Q is 1 divided by P conjugate. Yeah, that's a reciprocal 0. Yeah, but now since P is on, yeah, I should say since P is not real. Yeah, I suggest that we actually also place a pole at P conjugate. So yeah, I suggest we put a pole at P conjugate. And then here, the 0 will be Q conjugate, which is 1 over P. Okay, yeah. So by doing this, we are basically cascading two all-pass filters of the first order. If we call that this is an all-pass filter of the first order, 一阶的啊. If this is a first order all-pass filter, then by pairing our pole with its conjugate, we have created a second order all-pass filter. Okay, so let's say now define. This is an extension. Okay, we can just if h of z is h1z, h2z, where h1z and h2z are first order all pass. Okay, comma. Okay, so let's take a look. If h1z and h2z each is a first order all pass filter, and then we cascade these two systems, then we multiply their system function. Okay, then we multiply their system function like that. The resulting system, the product system, will also have a constant magnitude response. When you cascade two systems of constant magnitude response, then the result, the product, of course, is also a constant magnitude response. Then, now this. The product system, then h of ej omega is simply h1 ej omega, h2 ej omega is constant times constant. This is a sloppy notation, but you know what I mean. The result is still a constant magnitude response. Okay, this is by constant 1, constant 2, so constant. So I'm just trying to say that if we have a lot of first order all pass systems, we can just cascade them indefinitely, as many of them as you want. Okay. Cascade and multiply their system functions. And the result will be guaranteed to have a constant magnitude response, because each subsystem is constant magnitude response. So if you just keep keep putting them in series, that's what I mean cascade, 串接, cascade, the word. Maybe I should write it down. Cascading. But cascading first order systems, and if each of them is all pass, the product is also all pass. All pass is the property of having a constant magnitude. Okay? So when we cascade several all pass systems, then the result is still all pass. Right? That's pretty clear. Right? So that's first to notice. This is simple. So then we can avoid having a complex value system by cascading an all-pass system with its conjugate system, having the pole and zero at conjugate location. When we cascade that, then if this is the case, then the resulting product will be real valued. Okay? All the filter coefficients will be real valued. This is about the polynomial, because when a polynomial have conjugate pairs, if their roots occur in conjugate pairs, then the coefficients are real. That's a very simple property. You guys look confused. 我用中文讲一次啊。多项式如果它的根是共二复数的话，它的所有系数都实数啊，就这样的意思。Okay, if a polynomial, if all the roots of a polynomial are in conjugate pairs, 共二复数 if that happens 的话then the polynomial is real value is a real a polynomial with real coefficients, and that's important. Because all the time, when we implement a difference equation, we don't want the coefficients to be conflict value. It's just weird. just weird. We can avoid that. It's pretty easy. We can avoid that by making sure that our poles occur in conjugate pairs. Okay. And for real pole and zero, if they're in reciprocal location, you don't need to do any extra thing. Okay. We don't have the problem. Okay. Yeah. So in general, you may have an all-pass system that looks like this. Okay. An all-pass system may look like they have a number of poles and a number of zeros. And each zero will correspond to a pole at a reciprocal location inside the unit circle. All zeros are outside. Okay. And some of the zeros can be real valued. Okay. It can be on the real line. So in that case, the corresponding pole is on the real line. Okay. On the x-axis. And for those of the zeros not on the real line, the corresponding pole is at the same angle, and we need to pair them with their conjugate to ensure that the corresponding difference equation looks good. Okay. To ensure that we don't have the trouble when we construct the difference equation, we won't see complex valued coefficients. Okay. So that's kind of a general principle. You can just, otherwise you can place as many poles as you want. You can place a pole right here and immediately pair it with a conjugate and immediately play it with a zero out there and zero out there. And we can extend by cascading our system with more pairs and more reciprocal pairs of poles and zeros. And the response will still be constant magnitude. Okay? Constant magnitude. All the frequencies will be given, will have the same gain. Yeah, all the frequencies will have the same gain. If you just follow this principle, you can construct all-pass system, right? Like that. So that's that's a nice kind of knowledge to know about. But next, I want to show you that. All-pass filter has also another nice property, and an important one, in that it's group delay. The group delay will always be positive at any frequency. The group delay of any all-pass filter that you might construct like that. Okay, turns out that any all-pass system that you construct like this will always have a positive group delay at any given frequency. Okay? And this is, so what we mean really, if you're serious about this, you can try, evaluating the angle of h of ej omega, right? So previously we have what? Like that. The angle of 1 minus 1 over p e j omega. There is minus sign. pp conjugate minus omega and 1 minus p e to the minus j omega. And take the arctangent real part, imaginary part divided by real part. If you are really serious about this, you can derive a explicit expression for that as a function of omega, and then try to blah 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 follow that by taking the first derivative, okay, to see if it's always negative. If the slope is always negative, you can try that at home, but I won't recommend that. Okay. It looks dirty. I mean, you might be able to succeed, but it looks dirty. But I know it is true. Okay, it's also in the textbook. The group delay is always positive for such kind of system that we can construct. So in the next homework, which I just started designing, okay, I will invite you to go through a derivation that surprisingly involves bilinear transformation. Okay? It turns out that this property is easier to prove when we go back to the analog domain, go back to the S domain. Okay, so please stay tuned. 敬请期待. Okay, please stay tuned. I have my own derivation. Yeah. So it turns out that it's easier to show via, I'm giving you a hint, via inverse bilinear transformation. And I promise you, this will be in your homework number 5, okay? Yeah, I have finished, I'm almost done with my design of the homework, yeah. Okay, but otherwise, keep in mind, this is a pretty strong property. Always having a positive group delay is actually a pretty strong condition for IRR systems. It doesn't always happen. Interestingly, it doesn't always happen. Group delay can be negative. In general, group delay can be negative at certain frequencies. Okay, So this is pretty strong property. Then we'll go through that, okay, next week, right? Okay, so next I want to indeed show you not the geometric interpretation, but let me jump ahead, okay? Because I want to talk about important stuff first. So now I've introduced to you that there is such kind of system which, even though the magnitude response is constant, the phase response is not a constant. But meanwhile, when you construct a system like that, putting reciprocal pairs of zeros and poles around on the plane, you can construct any system like that, and surprisingly, you're guaranteed to have a system with a positive group delay for any frequency, and that's a pretty strong condition. Okay. But next thing I want to switch to the topic before we leave today. I want to first talk about high pass and band pass. What are the design rules? Okay, the design. So as I mentioned on the board right here, it's a very simple idea. Couldn't be simpler. Okay, very simple idea that when we have a low pass system to begin with, if h of n is the impulse response of a low pass filter, then simply by multiplying h of n with -1 to the nth, okay, simply sort of modulate our system by changing the sign of every other sample in that impulse response. Changing the sign of every other sample, then we get a new impulse response. And it turns out that when we take the Fourier transform, you'll see that g of omega, when we go through Fourier transform like that, okay, you'll see that the frequency response is gonna be a high pass. Okay, why? The reason again is shift theorem. Okay, shift theorem. So let's go through this together. Okay, it's actually pretty easy. Why this is going to be a high pass? The first thing to notice is that -1 to the nth is a periodic signal, right, itself. It equals to e to the j pi n, right? E to the j pi is -1, right? So this is a signal at frequency pi, right? And we're multiplying our h of n with a complex exponential function, right? So immediately we can apply the modulation theorem, which means that when we multiply this in time domain, the result is going to be shifting in the frequency domain. So therefore, g of omega, like that, okay. G omega, this is a sloppy notation, but actually we are going to say g of ej omega, which is a dtft of g of n, which is that will be equal to h of omega shifted to the right by pi. No, to the left. Doesn't matter. Yeah. Shift by pi is going to be minus pi. Okay? Or same thing, plus pi. Why? Because any DTFT has a repeat itself every 2 pi. Okay, so you can just shift it to the left by pi. The result is going to be same as shifting to the right by pi. Okay, so that immediately changes your low pass response into a high pass response. Did everyone see that? Yeah. When we draw that, let's say this is our low pass filter. Okay, I try to give a careful job, right? Do a careful job, right? We may have ripple. Your design may have ripple. Yeah, FIR if it's FIR. Okay, typically having 0. Or if you have IR, you may have a Butterworth. Doesn't matter. Butterworth has a nice property of monotonically decaying Manning's response, right? Yeah. But either way, here I'm using this. This might look like an FIR. I agree. Yeah, this is an FIR. Let's say this is an FIR. FIR low pass. So now when we shift it to the right by pi, right? What's the result? The result of shifting this to the right by pi becomes a high pass filter. Yeah. Now the pass band is going to center around frequency pi. And with a cutoff frequency of pi minus omega c, right? So if you will draw some ripple right there, and there's a bandwidth which will appear at your left, because that's how DTFT really is. It always reappear at the other side of the frequency axis. Any DTFT repeats itself every 2 pi, right? So I'm saying that, okay, while you're still drawing, make sure that this part becomes this part after the transformation. And this part becomes this part. Okay? Do I repeat that? Yeah. Please take a look. Yeah. I'm going to show you. Yeah, please stop writing. This part becomes this part. And this part becomes this part. After shifting the entire frequency response to the right or to the left by pi, doesn't matter. Okay? Now already low pass becomes high pass. Okay? That's a simple derivation. When we multiply our impulse response in the time by -1 to the nth power, like that, okay, that gives you a high pass filter. If you start with low pass, this very simple procedure changes your filter into a high pass filter. Okay? And this is really wonderful. Okay? So suppose that, for example, when we design an FIR filter, right, like yesterday, when we had the kind of discussion we had on yesterday. So, for example, if your system, if your filter is, let's say, truncating the ideal low pass response with, you can multiply your ideal low pass response. You can multiply your ideal low pass response with a Kaiser window of, Kaiser, right? Kaiser window with beta, right? Oh. 好，下课。A Kaiser window, yeah. Just recap, right? Yesterday we were talking about FIR design by multiplying the sinc function with the window function, such, right? So the result might look like. So after that, you have an IR filter, which we call H of n, okay? Which we'll call H of n, which may look like that it's almost truncating. And it's still symmetric. Yeah. So you have a FIR filter. But I'm suggesting that now, with this, we change the polarity. We change the sign of every other sample. Seriously, yeah. So your design of a high-pass filter will be same for time zero, but changing the sign alternately 交错的 you will alternately change the sign of every other sample like that. Same plus minus plus minus like that. Change the sign of every sample of your old design, and then this new design G of n is gonna be high pass. Yeah, end of story. Yeah. So that's a very nice trick to know about. Okay? Yeah. Seriously, that's what we mean. Yeah. If we combine what we just learned yesterday, FIR design, right? Then you have a filter of certain length from minus n to n, zero phase. Okay. Of course, you can shift it to the right to make it causal. Doesn't matter. But even after shifting to the right to make it causal, still we suggest that we change simply by changing the sign of every other sample. Then you get a high pass filter. Okay, and it's guaranteed, and we know the reason. Okay, you do get a high pass filter. Okay. Then from here before we leave, we can have two discussions. Okay. First is then how about IIR? How about IIR? In FIR, then once you get your filter H or G, yeah, then you can convolve with your input with G of n. Just convolve them, the system produce output. Okay, this is a high pass filter. Yeah. For FIR, it's pretty clear. But how about IIR? How about IIR? Yeah. That's the first question, okay, that I'm listing right here, okay. However, how do you design, if h of z is bz divided by az, then how about g of z? What is g of z? Yeah. If h of z is bz divided by az, that's an IIR. When az is a polynomial, then we have an IIR, right? Yeah. So if bz divided by az represents a low-pass filter, how do we change it to a high-pass filter? In terms of implementation, we know that this is the result we want to achieve. We want the new system to relate to the old system by this relation, by the relation that every other sample changes its sign, right? But how do we make it happen in the z domain, in the difference equation domain, right? How do we change the system? How do we change it? Or how do we change, in other words, how do we change the difference equation? The difference equation so that the result is a high-pass filter, okay? And this is in the textbook, but it will also be in your next homework, okay? In the next homework, I'm going to ask you, I'm going to suggest a very simple way, and I'll ask you to prove it. Okay? I'm going to suggest a very simple way that the answer is that simply g of z is h of minus z. That will be the end. Okay? Yeah. So it turns out it's that simple. It's really that simple. Okay? I asked you to show that. Okay? But this operation will change. We can change an IIR system, a low-pass IIR filter to become a high-pass IIR filter. Okay, yeah. So that's part of your homework 5. But now, seriously, probably we're running out of time. But the general principle that now you have learned how to design a low-pass filter, right? Now we have learned how to design a low-pass filter. Let's say it has a color frequency at omega c2, right? And you also learn how to design a high-pass filter, right? Like that. Let's say ripple. If you know how to design a low-pass filter, you know how to design a high-pass filter, automatically you should know how to design a band-pass filter. Simply putting them in cascade, right? First low-pass, then high-pass, or doesn't matter. Or put them in parallel. first low pass and there's another path, 一个其他的路径 to produce high pass, then you have, or you can even create a system like that with h of z on top, g of z at the bottom, and you have low pass on top, high pass at the bottom, and then you sum them. Then you may have a system with two pass bands, right? You may have low pass and high pass, so it looks like a band reject system. So you have many different possibilities. Okay, you can have many different possibilities. Once you know how to design low pass, how to design high pass. Okay, so the rest is just pretty straightforward. Just need some experiences. Okay, so I'm running out of time today. Please enjoy Mother's Day. You can go home and meet with your mom, say you love her, or if possible, if possible. And otherwise, when we come back, next week we'll have a. Unfortunately, I'm gonna announce a new homework over the Mother's Day weekend. Okay. Sorry about that, but you'll see some exercises with all pass system and low pass and high pass. Okay, so that's all I want to share with you. Thank you for being here, and see you next week.